Good morning. Can everyone hear me okay?
Yes.
Okay, 'cause I don't need a microphone. Welcome to my presentation. It's predicting the bank prime rate and exploration of RNNs. Again, my name is Larry Johnson. I'm a third-year college student, graduate student in the College of Engineering, the Master of Science of AI program. I have an undergraduate degree in information science from University of Pittsburgh. And by day, I'm a software engineer. I've been doing it for several years now. I'm not going to say how many. In different capacities, architecture, management. Now I'm an independent consultant where I do software development for large corporations. Our agenda today, we're going to kind of just talk about the problem statement briefly, then talk about some EDA, or exploratory data analysis, talk about model training and evaluation, and then some next steps as well. And I'll also leave some time for questions as well towards the end. So if you can save questions for then, that'd be great. So problem statement, what am I trying to solve? So in today's highly effective market, in terms of like global economy, there's so many moving parts. Macroeconomically, you got CPI index, you got the Fed for doing monetary policy, you have the stock market, and you also now have crypto, which is interesting. So we're going to talk about how we can use RNNs to do predictive modeling for machine learning using non-standard traditions like statistical methods. So I'm not going to go over this slide, but it's explaining how detailed, how complex today's economy is. There are so many moving parts that it's too many to name. And every day some new asset class comes on that we don't even understand, and it disrupts the markets. What I did in my research was to distill down those high-level factors into 5 features. The CPI index, consumer price index, is kind of looking at inflation. Bitcoin to represent crypto markets. S&P 500, federal funds rate, and also 20-year like bonds, treasury securities. And so if you look at that, these are like proxy factors for the economy. And then I'm trying to predict the bank prime rate, which is like 3% above the federal funds rate. So for those who don't know, the federal government lends money to banks at a discount rate. Then banks lend to each other overnight through the federal funds rate. And then they lend to us at a bank prime rate, which is like 3%. So by the time you get a mortgage or a car loan, something like that, it's above what the banks are making to make margins on their lending products. All right, so this is kind of a showing you a time series of all the different data sets from the 1950s until 2025. And next slide we'll talk about the actual modeling I actually did for the different time series. But you can see it, all these series all over the place, right? Nothing looks very consistent. And also, when it comes to data, if you look at from the beginning of the time series till now, you're seeing more and more and more, they call them black swan events. So there are events that happen in our market. There's a gentleman named Nassim Nicholas Taleb, wrote a great book called Black Swans to talk about these improbable events. They happen more and more and more. If you look at the time series, they mostly start happening around the 80s, which is around Reaganomics or deregulation. So obviously, a model can't predict the future, but based on what's available, it can look at what's in the past. They say quantum computing will fix this someday. I don't know, but we'll see. All right, this is showing you distribution of the data, how it looks. None of it obviously looks the same. These are the 5 different data sets: CPI, federal funds rate. They also, a lot of them look very unnormalized, right? But if you take the first bin away, if you look at the top right, the federal funds rate, it kind of looks like a normal distribution to some extent, but again, data is all over the place. There's some outliers, but again, the data is very different. Now, this is showing you the correlation. So a correlation matrix is showing you, basically, you interpret this little lot going on here, but between 0 and 1 is the number. 0 means there's no correlation. A negative means it's negative correlation, like one's going up, one's going down. And positive means it's going in the same direction. So in the data set, highly correlated, you can see, is S&P 500 and Bitcoin. Negative correlations, S&P 500, Bitcoin, and CPI index. The point of this slide is showing you that the data is highly correlated in certain places. Some of it has low correlation. Some of it has a medium amount of correlation. But ultimately, if you look at some of this data, like in the previous slide, look at this one here. Over the years, Bitcoin was normally a hedge for inflation, which it still is as well today. But if you look at the actual the R correlation, it's trading like a stock. So if you're trying to save for retirement or maybe educational things, Bitcoin is an asset class. It's a valid asset class. It's here to stay. Not sure about Ethereum and other type of alternative stable coins, but cryptocurrency is here. Whether we like it or not, we should use it in our portfolios. Feature engineering that I did for this data set, just kind of going through piece by piece. Let's look at the top left. For the actual training that I ultimately did at the end to choose the different modeling techniques, I started between January of 2012, and then I ended in December 31st of 2024. And some of the data came in at varying intervals. A lot of it came in as monthly, like 'cause a lot of data from the Fed, for example, is they're going to give it to you every month. And it is kind of, unfortunately, a lagging factor, so like a month behind normally. But it comes in monthly. Bitcoin was like, obviously, you're looking at trades, like on blockchain, things of that nature. I got it down to the minute level, but I had to bring it up to the daily level to a rolling average. And I use interpolation for the other monthly values. And interpolation basically is like what it sounds like. You have one data point here, another one here. You don't have everything in between. You're trying to interpolate it, like what is actually happening. So it's kind of helping you to look at the pattern of the data. And also, I did min-max scaling, which basically means these values are very different, right? If I look at S&P 500 compared to the Fed, those numbers are very different, right? To normalize it using a min-max scaler, it puts everything between 0 and 1. So when I put on the same scale, I can do predictive modeling without having too much, overfitting. And then I'm not going to talk about this in too much great detail because Professor Orhan knows RNNs take a whole semester to describe. So I'm going to try to do it in like 30 seconds if I can, if you will. Look at the top left. We're talking about deep learning. Most of the time it's going forward, right? On a forward pass. I'm trying to look at some values. I'm computing the matrix, and I do back propagation, but it's always going forward. With recurrent neural networks, it's coming back into the model for that hidden state, and it's being used to predict the output. They call it autoregressive models because you're using the past to also predict the future. Unrolled, they're kind of showing you here, where if you see it on the top right here, this is kind of the important part of RNNs, where it keeps like this short-term memory because it's passing in those previous weights to the next connections. And then the bottom left is showing you what the LSTM units look like as they're being passed from each hidden state to the next hidden state. And then internally here, they're showing you what an LSTM unit is. And the F basically means the forget gate, which is determining how much of the input to forget. The input gate, how much of the input to keep. And then the output gate is keeping that long-term memory ultimately. So the forget gate, the in gate is kind of making up that short-term memory. And then the output gate is that long-term memory. All right, can you see this? It's a little small. I'm not sure if you all can see that. I'm going to have to probably use the mouse a little bit. So this is the model I ultimately settled on. I did a few different models that I tested with. I had a 3-layer model, the input layer, which obviously is taking in your inputs for your features. Then you have your LSTM cell that's running in here. And then I had like the dense layer, obviously, to get that continuous value at the end, which was the federal funds rate. And it's kind of also displayed. It's a little small, so I apologize. It's a little small to see that up in here. But it's just showing you all the different things that are being computed in the process. I used 16 batches, and then my time steps were ultimately for my last model, the lags were 30, 60, 90 days. What that means is I'm looking back 30 days, 60 days, 90 days in the time steps to predict the next value. It's my learning rate was 0.001. I used about 100 epochs during the training step. All right, this is a little small. Can you see it clearly a little bit? Are the numbers coming in okay, or is it hard to see? Okay. All right, it's hard to see? Okay, I'll do my best to explain it. So the middle part here is really what did the best. So all these different models, there are different types of LSTM models that I tried out. Some were monthly lags, some were daily lags. The model that performed the best for the initial data set, so I tried to predict, like, I took the data set from 2000 till 2024, and then I basically started 2025, and I tried to predict what happened in January. So the 4-layer CNN LSTM did the best at 60-day lags, but ultimately the model that really performed the best, you'll see on the next slide as well, was this 30-day lag. I tried to predict the federal funds rate, which was 4.33, but I ended up getting 4.47, and my error rate was 0.14, which is not a bad model considering. The CNN layer as well. The 4-layer did decent, but again, ultimately I use these two at the end to compare it. The 7 layers bidirectional LSTMs, comparatively speaking, perform very poorly. So this is telling you, if you look at the data, less is more. So more when you're dealing with a time series data for this particular data set, 3 layers were very optimally computed. And on this slide, this is showing you, to explain what I did here, I basically took the training data set from 2000 to December 31st, 2023. And then I tried to predict for that whole year a daily prediction from January 1st until December 31st. The mean absolute error was extremely low with the LSTM. Again, the one that performed the best was the 30 days. It had a mean absolute error rate of 0.0032, which is phenomenal if you understand the error rates. The LSTM CNN also did better. Not did better. It did just as well, but to me, adding extra complexity is probably not worth it. So these are showing you on this slide the LSTM for 30, 60, 90, then overall predictions. And that next slide is showing you the CNN. But if you can see it, I'll go back and forth, you can kind of see how the CNN kind of leaves off the line a little bit, which is telling you the regular LSTM model is more effective. Conclusion, less is more. The takeaway, daily lags did much better than the monthly time steps. Overall, the mean absolute error was low across all the different scenarios. The ultimate goal for this too as well is that you don't use these models to try to say what the Fed rate will actually be. This is more of a getting close to that number as possible. So if you're going to make a decision around lending, maybe you want to buy a house or buy a car, this is giving you that data to give you an idea of what the rate would be in the next month. Next steps, I need more data. I didn't use like unemployment data, for example. Professor Orhan kind of gave me some feedback. Use more data. That we're missing other data sets. Maybe add some more currency to it. There's definitely more accuracy improvements that we can use. I also want to try using GRUs, gated recurrent units, which is basically a simpler version of LSTMs. Maybe even try a REMA, which is like a traditional type of model. It uses kind of based on linear models, but still it'd be just nice to see, is LSTM better than traditional models? Also, I want to deploy to AWS, do an actual prediction in AWS, and actually see how good I do. Have it run every day or every month or whatever, and see in real time, how does this model predict against historical data? And then also at some point, I do want to publish my findings through research. That's it. Thank you. Any questions?
We don't have a lot of time.
Okay. Okay.
But I want to question to Larry.
All right. We'll be asking 2 questions.
Yes.
Yeah. First, let me start with the minor question. I guess you have also tried mean square instead of mean absolute. Yeah?
Yes.
So just penalizing those
The high number. Yes.
so far away.
Yep.
So how were the results?
The mean absolute error you're saying?
Yeah, mean square results.
Oh, I didn't do mean square. I didn't do mean squared.
You didn't?
I just do mean absolute.
Oh, I see.
Yeah. So I mean that's also an improvement, right? So when I look at this data, I just did mean absolute because I normalized the data, right? I did min max scaling, so I felt that kind of helped a little bit. But to your point, mean squared error could also be a good way to determine.
It helps, I mean, when you normalize, but when you're predicting towards distant future,
Yeah.
many days, then that will be penalizing those predictions that are not to the target for. So it will
That's
help
true.
actually.
Yep, I agree.
I have one more question, if you don't mind. So that this federal funds rate is the rate by which the commercial banks are lending and borrowing
Correct.
on themselves.
Overnight, correct.
Yeah, overnight. Yeah, but in a typical economy where the central bank is governing the entire economy, it's the Federal Reserve in the United States, but in other countries it's the central bank.
Sure.
They're using the discount rate actually, and that's the rate by which the Fed or the central bank is charging when they're loaning.
Correct. Correct.
You didn't use it here actually.
Correct.
That's the other thing.
Yep. Yeah. So so the goal for this project was the bank prime rate. So you have the discount rate, which is what the government uses to lend, like you said, to your point, to banks, and then you have the federal funds rate, which is the overnight rate they're lending to each other, and then you have the bank prime rate. So if I use the discount rate, I'm like 2 layers beyond where I would like to be for this particular application. So if I was trying to do discount rate, then I would have probably done a different route. So this is more or less if you want to, for example, make a lending decision, maybe you want to buy a car or a house. I'm more trying to help out from that perspective of on the commercial lending side of it. Did that help? Okay.
I have a question.
Yes.
If you could run this again in a few months based on the current shenanigans that
Yes.
are happening, what do you think results will be? Will they still be similar just because you're still using daily rate?
Exactly, yeah. I think it'll be similar. So the problem with the Fed, they publish data so late. That's the issue. So I'm always going to be still a little bit late, but I think it would be similar. Assuming you have all the data, for example, let's say this data went for January. Let's assume that it's January and February hasn't happened. I could still run the model to get some level of accuracy. I think it would be still close, right? But improbable events, right? Something major happens within the markets. We saw the Dow was like 1,200 points difference, like in like a day or two, because of this whole trade wars that are happening with these different countries. But I think it'll still be close. The error rate was still low,
Right.
so I think it would be actually still very close. Great
Okay,
question.
second question really quick then. Do you think that a secondary feature that you could add would be something to try to quantify current events? I don't know magically how you would, but
Sure.
the Reaganomics back in the 80s, 1998
Yeah.
dip, the 2008 dip, how would you, there'd be an interesting way to have it a non-quantifiable item
Yeah.
and how it affects. I was just wondering.
I mean, if you think I'm still, even today's market, I'm a fundamental investor. So I believe to some extent of the efficient market hypothesis. I still believe in EMH to some extent. Everything that happened in the market today is already priced in, right? You can't price for the future. And I think that's where institutions get in trouble. These models aren't meant for you to empirically say it's going to be this. You have to leave room for error, period. So ultimately, having that extra, buffer, I think will allow you to consider those things you don't know about. But yeah, I mean, I think the markets are understanding the only way to make money in today's market is leverage. But that's also very risky. So leveraging, we've seen what happened in mortgage meltdown, credit crunch. Leveraging 30-to-1 is a recipe for a disaster. So again, use this to me as a tool of approximating where it would be, helping to inform your decisions. Does that help? I'm not sure if I answered your question. Okay.
I have a question.
Yeah.
A couple of suggestions.
Yes.
First of all, you should definitely provide some motivation about why you are trying to predict the funds rate. I mean, as Dr. Roman said,
Sure.
why not this kind of? It's fine. I mean, you decided to audit, but just provide some motivation for the readers. The second thing is, so are you using the coin prices here?
I am.
Okay, you are using the level of the price, right? The price itself, not any difference, right? Or
Just the price itself, yeah. So I'm using also the daily rolling average. So Bitcoin's minute by minute. I'm gonna roll it to every day.
As a suggestion.
Sure.
In these kind of data, it is generally assumed that, not assumed, but it's shown that music prices are producing superior results.
Okay.
Like, for example, look at your correlation. The correlation between the S&P 500 and Bitcoin is 92. Okay, for 92.
Yep.
Which probably is spurious. Like, it's not real. It's hallucination. So that's why you should use Bitcoin returns plus S&P 500 returns instead of price levels.
You're saying return. So you're saying use the returns, internal rate of return,
Yes.
instead of the prices.
Yeah, Bitcoin
That's not a bad
You
idea.
might say, hey, what will be different?
Sure.
You will probably receive a lot of criticism from referees about using prices because, yeah, this is called superior results.
Sure.
Don't use prices in these kind of settings.
One question for that: do you recommend the nominal rate or just the actual the internal?
Doesn't
Either. Okay.
That's one. Everyone wants to know this test.
No worries.
Another question, guys. I think it's I said now because I appreciate it so much. Oh yeah, I remember. The third one is you should definitely compare your model with something else to say that this is good.
Like ARIMA, you mean, or?
Yeah. It might be Arima, it might be, I don't know, neural networks, it might be, I don't know, chain, whatever. So you are saying that this is low, right?
That's fair.
We not low to what?
I agree.
Somebody can produce another result which might be 10 times more 10 times better or 10 times worse than yours. You might say, hey, my model is good based on this model.
Yeah.
Right? Well, you can say something like comparative.
Yeah. That was one thing that I think Soka's takeaway as well.
I saw that.
I definitely need to do that, 100%. Empirical evidence, obviously, in research is important.
Otherwise, everyone would say that, hey, it's
Agreed.
low compared to us.
Agreed. Yep. I agree.
Any other questions, guys? Yeah, thank you so much.
Awesome. Thank you.
Yeah.